In this video, and a couple other ones, we're going to look at how ions can be classified as acidic, basic, or neutral. Now, up till now, we've been dealing with acids and bases that can be pretty clearly identified as such. But if we were given ammonium chloride, we would have classified that as an ionic compound, not as an acid or a base. But it turns out the ions that make up the ionic compounds can themselves be weak acids or bases. And so we know NH4Cl is ionic, and so when it dissolves in water, it's going to dissociate into ammonium ions and chloride ions. And when we were first introduced to the concept of Bronsted-Lowry acids and bases, we classified ammonium as the conjugate acid of the base ammonia. And we classified the chloride ion as being the conjugate base of the acid HCl. And so the fact that we're calling these conjugate acids and conjugate bases implies that they can in fact themselves be weakly acidic or basic, or they could also be neutral. And so if I'm considering an acid and I look at its conjugate base, the strength of the acid and its conjugate base are related. And the stronger the acid is, the weaker its conjugate base is going to be. So the stronger the acid, the weaker the conjugate base. In the case of something like HCl, it's such a strong acid that its conjugate base, Cl-, is so weak that it's in fact neutral. But if I have something like hydrofluoric acid that is a weak acid, its conjugate base is a little bit stronger, and so not only it's no longer neutral, and in fact itself is going to be a weak base. And then the same thing is true about bases. The stronger a base is, the weaker its conjugate acid is going to be. And the Ka and Kb of a conjugate acid-base pair are related by this equation. That's very similar to when we introduced the hydronium and hydroxide ion concentration being equal to Kw. Well, if I have the Ka of an acid and multiply it by the Kb of its conjugate base, that has to be equal to Kw. And so just to summarize what we're kind of talking about on that last slide, if I have a conjugate acid-base pair, and if the acid is a strong acid, then its conjugate base is going to be so weak that it's in fact neutral. If I have a strong base, its conjugate acid is going to be so weak that it's neutral. But if I have a weak acid, its conjugate base is going to be a weak base, or if I have a weak base, its conjugate acid is going to be a weak acid. So the anion component of an ionic compound is potentially going to be basic, or it's going to be so weak that it's in fact neutral. And so the way to figure out whether an anion is going to be basic or neutral, I need to find the conjugate acid. If the conjugate acid is a strong acid, and this is again where you need to know the 7 strong acids, then the anion is going to be neutral, right? The acid was so strong that its conjugate base is neutral. But if we find that the conjugate acid is a weak acid, then the anion is going to be a weak base. So I've got 2 examples here. I've got Cl-, so I need to find its conjugate acid. So if I add an H+ to that, I get HCl. We know that HCl is one of our strong acids. So if HCl is a strong acid, that means its conjugate base, Cl-, is going to be such a weak base that it's in fact neutral. All right, and when I take the acetate ion, its conjugate acid is going to be acetic acid. And acetic acid is not one of our strong acids, so it's going to be a weak acid. If acetic acid is a weak acid, then its conjugate base is going to be a weak base. Now, cations are going to potentially be acidic. And so I think the obvious question comes up, well, how could aluminum 3+ be acidic? It doesn't have any hydrogens to donate. Well, much like the hydrogen ions, and we know that it's more correct to think of those as being hydronium ions, where they're associated with water molecules, the same thing happens with metal cations. They are often associated with water molecules, and they actually form these complexes. And so this aluminum water complex has the ability now to donate protons. And so it's not the aluminum by itself that's donating a proton, but it's the whole aluminum water complex. So this is how cations can act as acids. All right, so the anions are either going to be basic or neutral. The cations are either going to be acidic or they're going to be so weak that they're neutral. So to find out whether a cation is acidic or neutral, I need to find the conjugate base, or in the case of a metal ion, I need to find its hydroxide. If the conjugate base or hydroxide is a strong base, then the anion is going to be so weak that it's neutral. But if the conjugate base or the hydroxide is a weak base, then the anion is going to be weakly acidic. So I've got two examples down here. I've got the ammonium ion, and it has a positive charge, right? It's a cation, so it's going to potentially be acidic, so I need to find its conjugate base. So the conjugate base of ammonia, if I take away an H+, I get ammonia, and ammonia is not one of our 8 strong bases. It is, in fact, a weak base. So that means its conjugate acid, the one that we're interested in, is going to be a weak acid. All right, so if it's not a metal cation and it has hydrogens that it can donate, we want to find its conjugate base. In this case, I've got strontium 2+. Here it doesn't have any hydrogens to donate, so instead we're going to look at the hydroxide. And so the hydroxide is, of course, going to be strontium hydroxide. And strontium hydroxide is one of our 8 strong bases. So if that is a strong base, then the strontium 2+ is going to be such a weak acid that it's in fact neutral. All right, so to this point we've just been looking at individual ions, but we can do the same thing for a whole salt. I just want to consider the cation and anion individually. And so I'll break the salt up into its component anions, or component ions, and I'll look at the anion and decide whether the anion is basic or neutral. And I'll look at the cation and determine whether it's acidic or neutral. In the easier problems, it's going to turn out that either they're both going to be neutral or just one of them will be acidic or basic. And if one of them turns out to be basic, then the salt is going to be basic. If one of them turns out to be acidic, then the salt is going to be acidic. It's a little bit more complicated if both the anion turns out to be basic and the cation comes out to be acidic. And this is something that we'll talk about in more detail during class. All right, so if we look at one example, so I want to classify sodium nitrite as being acidic, basic, or neutral. So what I need to do is first decide what ions do I have present. All right, so I know that I have NaNO2. When I dissolve that in water, it's going to break up into sodium ions and nitrite ions. All right, so if I consider the sodium first, it's potentially an acid. Right, the cations are potentially acids. Right, so I need to find its hydroxide, and so that's going to be NaOH. Right, now NaOH is a strong base. So that means that Na+ is going to be such a weak acid that it is in fact neutral. So the Na+ is not going to affect the pH, it's going to be neutral. Right, my anion is potentially going to be a base. So if I want to know about NO2-, I need to find its conjugate acid, which is HNO2. Nitric acid, HNO3, is one of our strong acids, but HNO2 is not. So if that is a weak acid, that means that the NO2- is a weak base. Right, so my salt contains something that's neutral and something that is a weak base. So that means that NaNO2 is going to be basic. All right, so this is just one example. But if you look in the description of this video on YouTube, you can find links to where I have lots more examples of both easy ones like this, where one's neutral and the other one is not. And I also have videos where both the cation is acidic and the anion is basic. And I also have further examples where we can actually calculate the pH of these salt solutions.